Welcome to my video tutorial about the properties of ionic structures. In order to explain what's going on, we have to remember that sodium chloride is made up of a giant ionic lattice. An electrostatic attraction between the positively charged cation and the negatively charged anion creates a very strong bond. Let's just recall that sodium is in group 1 of the periodic table. It has 1 electron in its outer shell. Chlorine is in group 7 of the periodic table, and it has 7 electrons in its outer shell. Sodium loses its outer shell electron, which is transferred across to chlorine. This produces a sodium ion and a chloride ion. As you can see here, the sodium ion and the chloride ion. In this form, you can see it's the giant ionic lattice, and between each of these ions, as I said, there's a very strong bond, and within the lattice there are millions of these strong bonds. What I'm going to show you is that we can use the charges on the ions, such as the positive and the negative charges, and the fact that there's lots of these strong forces of attraction between the negative and positive ions, and we can use those ideas to explain the properties of our results. So let's have a look at our first property. To answer why ionic substances do not conduct when solid, we need to have a look at the structure of the solid more closely. When in a solid, the ions for sodium chloride are fixed in the lattice and they can't move around. So when we connect up a power pack with a bulb attached to it and we put our electrode probes into the solid, the ions are not able to move from one electrode to another because they're fixed in this lattice structure of positive and negative ions. So we can add this now to our table. Okay, so let's have a look at our second property. So why do ionic substances conduct when aqueous? Well, let's have a look at that model again. Okay, so we saw that when solid, the ions are fixed in this lattice. However, when we dissolve our ions or we heat them up so that they're molten, the ions are actually now able to move around. That means if we were to connect a power pack up with a bulb and we popped our electrodes in, our ions would be able to move to the electrodes, and therefore they'd be able to carry a charge. So we can add that now to our table. Okay, let's have a look at our third property, high melting point. To explain this, let's go back to our original model. Okay, let's have a look at our ionic lattice in more detail. I mean, this here is just a small portion of an ionic lattice. They are much larger than this in reality. There are millions of positive and negative cations and anions electrostatically attracted to each other in a giant ionic lattice to actually create what we know as table salt. Within the lattice, each electrostatic force of attraction between these oppositely charged ions is extremely strong, and so when you start looking at the enormity of a lattice, there are lots and lots of strong ionic bonds, which is why we need a lot of heat to actually melt this structure. This means they've got very high melting points. And we can add this to our table. Okay, let's have a look at our final property. Ionic structures are brittle. So let's have a little look at why that is the case. Ionic bonds are the electrostatic force of attraction between oppositely charged ions. If you were to exert a force on an ionic substance, i.e. hit it with a hammer, what happens is that this ionic lattice breaks, and as the structure starts to slide, you end up getting like charges next to each other. Now, opposites here attract, but when you've got like charges next to each other, they repel. And what ends up happening is that the crystal will eventually crack. So let's add that final bit of information to our table. What I'd like you to now do is to complete the worksheet ready for next lesson to show that you understand the properties of ionic substances. So make sure you bring this in with you next lesson. I hope you found this informative. I'll see you soon.